Hello, young scientists. Did you know that some sounds are just too high-pitched for our ears to catch? It's like trying to hear a mosquito's secret conversation. Impossible. This is the world of ultrasound. Ultrasound refers to sound waves with frequencies above 20,000 Hz, way beyond the top note humans can hear. Because these waves are so high frequency, our ears simply can't pick them up. But don't worry, machines love them. They're widely used in medicine and industry to look inside things without cutting them open. Just like how ripples spread out on a pond, these waves need a medium like air, water, or solids to travel through. But since their wavelengths are really short, ultrasound waves travel in narrow, focused beams almost like a laser pointer rather than spreading out everywhere. And how do we make these sounds? Using special devices called piezoelectric transducers, they transform electrical energy into quick, tiny vibrations, producing these amazingly high-frequency waves. So, although you can't hear them, ultrasound waves are busy working behind the scenes in many cool technologies around us. Let's dive deeper into what makes ultrasound waves so special. Imagine a flashlight beam. It shines straight ahead, not all over the place. That's like ultrasound waves, and they're highly directional, shooting forward in tight beams due to their short wavelengths. Because of this, they hardly bend or spread out much, which we call negligible diffraction. Another neat trick: ultrasound can slip right through materials that are completely opaque to light. Think of a metal block. Light bounces off, but ultrasound can enter and bounce back from inside details, giving us clear signals from boundaries or flaws. But here's the catch: the higher the ultrasound frequency, the more it loses energy as it travels. This loss is called attenuation. So, very high frequencies can't penetrate too deep into dense materials. Now, remember the crucial relationship linking wavelength to speed and frequency? Wavelength equals speed of sound divided by frequency. In other words, lambda equals V over F, where lambda is the wavelength, V is how fast sound moves in the medium, and F is the frequency of the wave. This formula helps explain why ultrasound waves have such tiny wavelengths, incredibly useful for detailed imaging and detection. Now, how do we actually make ultrasound? Meet the piezoelectric crystals, like quartz, are superstar ultrasound producers. These crystals have a magical ability. When we apply an alternating voltage, they start vibrating back and forth at super high speeds, like an electric dance party. The frequency of the ultrasound depends on the crystal's natural frequency, which isn't random. It follows a neat formula. The frequency equals 1 divided by 2 times the length of the crystal, multiplied by the square root of tension over mass per unit length. Basically, F equals 1 over 2L times the square root of T over mu. It sounds complicated, but think of it as tuning a guitar string. The length and tension control the note produced. When we apply an alternating current, AC, at the crystal's natural frequency, something magical happens: resonance. The crystal vibrates with huge amplitude, making ultrasound waves loud and strong. But to get this right, the device has to be carefully engineered. If it's off, the ultrasound output will be weak or off frequency. So precision is the name of the game here. Here's where ultrasound really shines, literally, in medicine. Ultrasound is the star of sonography, or ultrasonography, where it creates real-time images inside our bodies. Ever wonder how doctors see a baby inside the womb without any pain or radiation? That's ultrasound at work. Since it's safe and non-invasive, it's perfect for monitoring fetal development during pregnancy. How does this magic happen? The ultrasound probe sends out waves which travel through tissues, bounce back from organs, and return to the probe. By measuring the time delay between sending and receiving the echoes, using the formula depth equals speed times time divided by 2, we can calculate how deep each organ or surface lies. Here, d equals v times t over 2, where d is depth, v is speed of sound in tissue, about 1540 meters per second, and t is the time delay. And there's more, ultrasound is used therapeutically too. Focused ultrasound waves can break up pesky kidney stones or help heal muscle injuries, all without knives or pain. It's like having a tiny sound hammer working inside your body, quiet but powerful. Ultrasound isn't just for doctors, it's a favorite in industry too. Imagine you have a metal part. How do you check if it has hidden cracks without smashing it to pieces? Enter ultrasound for non-destructive testing. By sending ultrasound waves through metal and listening for echoes bouncing off internal cracks or impurities, we can spot faults as small as a hairline. Plus, ultrasound causes tiny bubbles called cavitation bubbles in cleaning solutions. These bubbles pop and scrub away dirt from delicate instruments like surgeons' tools or jewelry without any harsh scrubbing. And here's a cool one. Ultrasonic welding uses those same high-frequency vibrations to fuse materials together by heating them up quickly, kind of like shaking hands firmly enough to blend into one. When echoes reflect from flaws inside metals, the reflection coefficient varies, so analyzing echo strength helps figure out the flaw size and location. Ultrasound is truly the invisible inspector and cleaner in many factories. Let's crack a quick example to see ultrasound maths in action. Suppose an ultrasound device detects an echo returning after 0.4 milliseconds, that's 0.0004 seconds. We also know the speed of sound in tissue is 1540 meters per second. To find the depth of the reflecting surface, we use our trusty formula, depth equals speed multiplied by time divided by 2. That's d equals v times t over 2. Plugging in the numbers, 1540 multiplied by 0.0004 divided by 2, that's equal to 0.308 meters. In other words, the reflector, maybe an organ or a bone, is about 30.8 centimeters deep. See how sound waves are like our eyes inside the body, measuring distances with precision? All thanks to timing, echoes, and simple multiplication. To wrap up today's sound adventure, let's refresh the key points. The speed of sound, v, equals frequency f times wavelength lambda. That's a golden rule for waves. In Kundrat's tube, wavelength lambda equals to times d, where d is the distance between adjacent nodes. That's how powder patterns reveal the invisible wavelengths. The rod's vibration frequency, f, depends on its speed and wavelength inside the rod. F equals V sub r divided by lambda sub r. Standing waves in air create fixed lycopodium bands, those dusty nodes that cleverly help us measure lambda. Thanks to resonance, the vibrational frequency matches perfectly between the rod and the air column, letting us find sound speed in air. And just like life, experiment accuracy improves when we average measurements and consider environmental factors like temperature, because sound speed changes with how warm or cold the air is. So remember, today we saw how sound waves invisibly etch patterns in powder, how resonance lets us tune between solids and gases, and how math turns these observations into numbers telling us how fast sound really travels. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.